Okay, for this section we're going to look at some limit laws. Mostly these limit laws are the same as for the case x going to finite value a. So if you compare, you'll see that they are very similar, just that now we look at x going to infinity. And here throughout, x going to infinity means either x going to plus infinity or x going to minus infinity. So just a shorthand. So let's look at the laws in detail. First one is the limit of x as x going to infinity. Actually, this should be infinity. The second one, the limit of a constant is just that constant as x goes to infinity. 3, limit of a sum is sum of the limits. And here we assume that the limits exist and are given by L and M. And then likewise, the limit of a constant times a function is the constant times the limit. The limit of a product of functions is the product of limits. Limit of a quotient is the quotient of the limits. And here you have to be careful. The limit that you put in the denominator should not be equal to 0. And then the number 7 here is the limit of a power is that limit raised to the power. And here you have to make the same caveats as for limit x going to a. So we want the limit of f of x, x going to infinity, to be bigger than 0 or equal to 0 for n even. So this has to be positive or 0. And the limit of f of x, x going to infinity, should be different from 0 for m negative. And then there are a couple more that I haven't summarized already that we can briefly consider. So the 8th one is if f of x is less than g of x, then the limit for x going to infinity fx is less than or equal to the limit of g of x. Number 9, the limit x going to infinity of 1 over x to a power n is 0 if n bigger than 0. And the last one, and that's a useful one as well, if you have the limit of a composition of functions, g of f of x, and you let x go to infinity, then that is the same thing as taking the limit of g of y, with y going to a certain value c, where c is equal to the limit of f of x as x goes to infinity. And here there are two conditions to keep in mind. The first is that c should be a real number, not plus or minus infinity. And the second one is that the function f should be continuous. So if you want to use this property, you have to check that the two conditions hold. So these are very useful properties to compute limits, as we'll do now. Most of the time you don't use them one at a time, but you'll get some intuition and then you'll use them rather quickly. But for the example, let's work things out a little bit more in detail and see what that buys us. So we'll compute limit x going to infinity of 2x to the 5 plus 1 divided by x5 plus x to the power 3 plus 1. If you just substitute infinity in there, and here let's take plus infinity, then if you substitute infinity, you'll get that this looks a bit like infinity divided by infinity, which sadly does not make sense. So we'll have to be a bit more rigorous in our calculation. So what we'll do is we'll first factor out the highest power. So we'll take the 2 times x5 here and the x5 there, and we'll bring them out as factors. So 2x5, 1 plus 1 over 2 to the power x to the power 5, and then likewise x to the power 5, 1 plus 1 over x squared plus 1 x to the power 5. And now we see an interesting cancellation. So this x to the power 5 and this x to the power 5 drop out. And now we can continue to compute. So we have limit of a constant times something. So that's 2 times the limit. And actually, let's also use the rule where we can take the limit of a quotient to be the quotient of the limits. So 1 plus 1 over 2x to the power 5, and then here 1 plus 1 over x squared plus 1x to the power 5. So here what we basically used is the limit laws 3 as well as 5. And so continuing with that, we can write this now as 2 times limit of the sum is sum of the limits. So we get limit 1 plus limit 1 over 2x5, limit 1 plus limit x squared, 1 over x squared, limit 1 over x to the 5th. And that's all going to plus infinity. So here we used number 2. And now we get some more interesting cancellations. So first of all, limit of a constant, that's just that constant. So this is 1 and this is 1. And secondly, limit of 1 over x to some power, that's 0. So this is going to be going to 0, this goes to 0, and this goes to 0. And we're left with 2 times 1 over 1. And here we have used the rules. Limit of constant, that's the first, and 1 over power, that's number 9. And so finally the result is 2. So now let's look back at our original problem statement. If you look at where this 2 comes from, you see that it was basically the coefficient that we had from the highest order terms. So what you can do is, if you have a rational function, is you can look at the highest order terms to quickly find the limit. So here basically what happens is, if we have our limit one more time, then as x becomes larger and larger, these two terms, 2 to the power x5 and x to the power 5, they become much larger than the remaining terms, and they dominate the remaining terms. So what we end up basically is that this limit is whatever you get if you neglect the terms that are not the highest order, and then you can see that this quickly becomes equal to 2. So looking at the highest order terms also works in more general cases than just pure rational functions. So for example, number 2, we look at the limit of x going to minus infinity of x to the power 7 divided by square root of x 14 plus 1. So if we look at the highest order terms, in the numerator that's x to the 7, and in the denominator it's x to the 14, but you have to take a square root. So if we do this real quick, we get minus infinity x to the 7 square root of x 14, and that's equal to limit x 7, x going to minus infinity. And now you have to be a bit careful. X to the 14, that's an even power, so what we get here as that's a positive, gives us a positive number. We take the square root, that's still a positive number, but keep in mind x here is very strongly negative. So if we take the square root of x to the 14, that's x to the power 7, but with an absolute value sign. And then if you simplify that a little bit more, that absolute value becomes minus x to the power 7, and you get x to the 7 divided by minus x to the 7, and the limit becomes minus 1. So let's do this again, but with the limit laws. Then we get minus infinity x to the 7, and then here we isolate x to the 14, 1 plus 1 over x to the 14. We take the x to the 14 out of the square root. We get x to the 7 divided by, and here you get again that absolute value, x to the 7 square root of 1 plus 1 over x to the 14. We can apply the same simplification here and here. These two cancel, and the only thing that you get is a minus sign. So we get limit x going to minus infinity minus 1. This square root. And now, again, limit of a quotient is quotient of the limits. X going to minus infinity. Now here, so again, we're using the quotient rule here, which is number 5, to go from here to here. And then we can write this as minus 1 square root of 1 plus limit x to the minus 1, 1 over x to the 14. And then we see that this whole thing goes to 0 because of our rule 9, and we end up that the limit becomes minus 1. And we see that we get exactly the same thing from the informal calculation by doing it step by step. And you see that the reasoning is the same as well. It's the highest order terms that matter. For the next example, we'll look at the limit of x going to plus infinity of square root x squared plus 1 minus x. If you just substitute plus infinity, you get infinity squared square root, that's infinity, minus plus infinity, so you get basically infinity minus infinity, and that doesn't do you much good. That's undefined, indeterminate, whatever you want. So if we want to calculate this properly, we'll have to do something. And what we usually do when we have square roots is we can multiply by the conjugate and see if that gives us something. So we put this fraction, and then we take the limit of this whole thing. So in the numerator, then we get x squared plus 1 minus x squared, and in the denominator, square root of x squared plus 1 plus x. This x squared cancels with that x squared, and we are left with x going to plus infinity 1 over square root x squared plus 1 plus x. If x becomes larger and larger, square root of x squared becomes larger and larger as well. X becomes larger and larger. So what we end up here is we get 1 over plus infinity, and that gives us 0. So writing something like this is a little bit tricky because infinity is not a number, you can't really calculate with it. But morally speaking, that's what happens. We do 1 over a very, very big number, so that gives us a very, very small number, and in the limit we get 0. For the fourth example, we'll take a look at the limit of e to the power 1 over x as x goes to 0 from the negative side. So here we have a limit of a function, and moreover we will see shortly that this is a continuous function. So we can write this as e to the limit x going to 0, 1 over x. Again, let's do this handy wavy. So x going to 0 from the negative side of 1 over x, that basically gives us minus infinity. So 1 over a very small number, that gives us a very big number, and it's a very big negative number, so we write minus infinity, and e to the minus infinity, that then becomes 0. So again, handy wavy steps, so let's do it a bit more formally. So here what we can do is rewrite 1 over x as t. So then this limit becomes e to the power t as t goes to minus infinity. And now we can use one of the properties of the exponential function, that it becomes vanishingly small when its argument goes to minus infinity. So just to remind you, if you have the graph of the exponential function, then if you go to minus infinity, the function becomes smaller and smaller. And in both cases, we end up with the same results in a formal or a slightly more informal way. A couple more examples. So the next one, let's take the limit of sine of x as x goes to plus infinity. There's no particular rule for this, so let's have a look at the graph. We know that the sine function oscillates between between minus 1 and plus 1, but it doesn't settle down on a definite value. So it forever cycles between minus 1 and plus 1. But as x goes to plus infinity, it doesn't really settle down on anything, so here the limit does not exist. And then for the last example, we're going to take the limit of e to the power tangent of x as x goes to pi over 2 from the negative side. So again, we can use one of our properties to say that exponential is a continuous function, so we can write this as e to the power limit of x going to pi over 2 from the negative side, tangent of x. Let's have a look at what this value then becomes, and in order to do that, let's graph the tan function. So we know it has vertical asymptotes at minus pi over 2 and plus pi over 2, and in between those asymptotes it looks like this. And in particular, we see if we go to pi over 2 from the negative side, so we get closer and closer to pi over 2 from the left hand side, and we see that our values become larger and larger, so we go to plus infinity. So what that means for our combined function here, the limit of tan of x, we've established that is plus infinity. So what we basically end up here with is the limit of e to the power y as y goes to plus infinity, and we get plus infinity as well. And then a last quick piece, infinite limits at infinity. So that's combining the two aspects. So here we have limits of the form x going to plus or minus infinity of a function f of x, and the result is again plus or minus infinity. And there's not really much new here. Most of these results you can read off either from the graph or from thinking what the values do. So let's look at a few examples. If we take the limit of x cubed, for x going to plus infinity, that's going to give us plus infinity, and for x going to minus infinity, that gives us minus infinity. So this notation basically means limit x going to plus infinity, x cubed is plus infinity, and limit x going to minus infinity, x cubed is minus infinity. But we sort of summarize it by saying plus minus. Similarly, if you take higher order powers, so x to the power 5, no difference there. But if you take a even power, x going to plus or minus infinity of x squared, the square will get rid of the minus sign, so in both cases this is going to be plus infinity. And another few examples, the limit of x going to plus infinity of e to the power x. We've already encountered this one, it's plus infinity. And then last one that is maybe a bit more work to calculate, x going to plus infinity of x squared minus x. So at first sight, again, this would tell you that it's infinity minus infinity. That doesn't really make sense, so let's be a bit more circumspect about it. So we can write this as limit x squared 1 minus 1 over x. Now we have the product of, or the limit of a product is the product of the limits. Like so. And then for limit of x squared, we already established that gives us plus infinity. And the limit here, 1 minus 1 over x, the 1 over x, that's going to go to 0. So here we have times 1, and so the result here is plus infinity. So to summarize, if you have to calculate infinite limits, then there's a couple of things that you can try. So the first thing that you can do is try just substituting the value plus or minus infinity. And see if that makes sense. And sometimes you get things like 1 over plus infinity, that's 0. Infinity divided by a constant, that's plus or minus infinity, and so on. So oftentimes, even if you want to do it more formally later, this is a good way to sort of see what the answer should be. If that doesn't work, if you get things like infinity minus infinity or infinity divided by infinity, then you have to try some manipulations. And the manipulations that we've seen so far are, well, try simplifying the fraction or the expression that you have to see if there's some calculations that you can take into account. There's also the trick of looking at the highest powers, and then something that is always a good idea if you have square roots, multiply by the conjugate. This is not an exhaustive list, so there might be other things that you can do which allow you to make sense of the result, but that depends on the situation. And then last, two special cases without proof. If you encounter the limit of sine of h divided by h for h going to 0, that is always equal to 1. And if you have the limit of h going to 0 of cosine of h minus 1 divided by h, that is 0. These are going to be super important when we start looking at derivatives, so I would give them a special place in your formula sheet, but not necessarily try to prove them yourself.